All right, so as I said before, thermochemistry is the study of heat transfers, energy, stuff like that. Okay, so let's look at our first problem. Is the freezing of water an endo or exothermic process? And we're going to explain. Before we answer this, though, let's review what endothermic and exothermic mean. Okay? What does exothermic mean? So it doesn't actually have to be a reaction. It could be any sort of process when we're talking about endo and exothermic. So exothermic just means that the system is losing energy, or energy is being released. Okay. So exothermic is energy is released. And more specifically, we're talking about in form of heat. Okay. And what about endothermic? It's absorbed. All right. So, freezing water. Freezing water. In order to freeze water, what is happening? Like what's happening to our water? It's going from what to what? It's going from liquid to solid. How can you describe what's happening to the particles of water? So what can we talk about their speed? They're slowing down, right? So in order to slow down water molecules, what must we do with energy? We have to take it out, right? We have to lose the energy in order to slow the particles down. So if we're losing energy, is that endo or exo? All tangled there. Yes, that is exothermic. So heat energy has to be removed in order to slow down those particles enough for them to freeze or solidify. Okay. A lot of this unit, in terms of like the conceptual part of it, is identifying what's your system and what's your surroundings, okay? And what's happening with energy with your system. Is energy going into your system? Is it coming out? What is it doing? Okay, that's a lot of this, the conceptual part of this unit. Okay, and that's actually, the math part of this isn't actually that difficult. I mean, yeah, it's a lot of math, but the math itself is not that difficult. What's the difficult part is identifying what math to do, which is really trying to figure out like what is your problem asking? What is it asking you to solve for? That's the challenging part. Once you know what you're solving for, then the math is easy. It's identifying your system and your surroundings that's the difficult part. Okay? So, in this one, in number 2, we are classifying each process as endo or exo. But I've already told you what the system is. Okay, the system is underlined in each example. So for this, you're identifying is the process, or in terms of the system, is it endo or exo? So if it's endo, that means the system will be gaining energy, and if it's exo, the system is losing energy. Let's do the first one together. Your hand gets cold when you touch ice. Okay, so your hand gets cold. Is your hand gaining or losing energy? It's losing, so therefore your hand, in terms of your hand, what is that? Exothermic. Because heat is being removed from your hand. Okay? So now go ahead and take a minute to figure out the other 4. All right, so now that you've had a chance to do these, for B, the ice gets warmer when you touch it. So the ice is our system. Is our ice endo or exo? Endo. Endo, because what's happening with the ice? Yep, it's absorbing that heat, or heat is added to the ice. All right, what about when water boils in a kettle being heated on a stove? Endo as well, because we're adding energy to the water. All right, water vapor condenses on a cold pipe. Exo. Yep, because when we condense something, we have to take energy out of it. We have to take heat out of it. Heat is removed. And ice cream melts. Endo. Heat is being added. So those were very straightforward, right? That was like a Chem 1 level type question. Yeah. Okay. So now the next part is identifying not only is it endo or exo, but also figuring out what your system and your surroundings are. Okay? So with this first one, we're going to define what our system is, what our surroundings are, and then state the direction of energy transfer or of heat flow. Okay? If it's going from the system to the surroundings, that means the system is losing energy, which would be exothermic. When it's going from the surroundings to the system, into the system, it's absorbing energy, that's endothermic. Okay? So, methane is burning in a Bunsen burner in a laboratory. So this is kind of like sentence structure, like in English class, where you have to identify your subject and your verb and your predicate. Is that a word? Yeah. Okay. That type of stuff. So what is our system for A? Methane, because that's the thing that's being burned, right? So this is our system. And what is our surroundings? Bunsen burner, in a lab, pretty much anything that's not the methane, right? All right. So, which way would energy be transferred here? Why do you say surroundings to system? Okay, it is initially absorbing energy from the Bunsen burner. This is true. There is. Only because what type of reaction occurs here? Combustion. This is a combustion reaction. Combustion reactions are extremely exothermic. They give off a lot of heat. Okay, so it is true that initially the Bunsen burner puts energy into the methane. Okay, but once that methane starts burning, it releases a lot of energy. Okay, have you ever seen a reaction profile that looks similar to this? Yeah, so here's my methane and my oxygen gas. And then what are my products? That's a 4. CO2 and H2O, right? So this part here is where we put it in the flame. What else is that called? Activation energy. So the flame provides the enough energy for the reaction to start. That's the activation energy. But then see how much it releases? And this is not to scale at all, but if you end up releasing or getting back out more energy than you originally put in, then it's exothermic. Okay? So really, our surroundings are more just the lab, and this is my activation energy. The source of my activation energy. Okay? So overall, methane burning is exothermic. It's going to release a lot of energy overall. Okay. All right. For B, water drops sitting on our skin after swimming evaporate. What is our system? There's no catch here. Water drops are my system. And what what are the surroundings? Your skin and everything else, right? Okay. So in order to evaporate those water drops, does it need to gain or lose energy? It needs to gain energy. Where does it gain the energy from? Your skin, which are part of the surroundings. So this would be endo. Because the surroundings are putting energy into the system. Well, that's why we did this problem, is to show you that it's like to discuss that. The problems on like the AP exam or on like any of your in-class quizzes, tests, stuff like that, it's going to be clearer. There isn't going to be like a something you should have known about that we haven't discussed. All right. So now let's do a little bit of calculations. Right? Yeah, we're at number 4 now. So, to calculate the change in internal energy of a system, delta E, we need to know both the heat of the system and the work of the system. Okay? So number 4 is talking about work, which does relate to energy. The delta E, the internal energy of the system, is the work and the heat combined. Heat is like this stuff that we were talking about. Okay? Work is a little bit more difficult to visualize. Okay? Now, to calculate work, we have this formula. And this was in your guided notes. Work equals negative P delta V. Now, something to keep in mind. This is our first, I think, this is like the first part of the year where we're actually seeing the delta, the change value or symbol. Delta is always final minus initial. Always. No matter what our delta is. If it's delta V, if it's delta H, delta T, whatever. It's always final minus initial. So it is possible to have a negative delta V if we're ending at a volume that's smaller than where we started. Okay? So work, actually let me back up. Heat. Heat gets the symbol Q. Okay? Q can be positive or negative. When Q is positive, that means it's endothermic. Okay? A positive Q means that the system is gaining energy. Endothermic. Q can be negative when it's exothermic. The system is losing energy, losing heat. So Q is negative. Work can also be positive or negative. This one's a little, like I said, this one's a little more tricky to visualize. Whenever a gas is expanding, whenever you have an increase in volume, then the system is doing work. Whenever you have a decrease in volume, then work is being done on the system. It's like a compression, work is being done on the system. But how that translates to positive and negative is, think about it this way. If you have a lot of work to do, you have to do a lot of work. That kind of sucks, right? That's a negative thing. When the system has to do work, it's negative. You're getting work done on you. You're getting a little touch-up, a little facelift, you know, whatever. That's positive, right? So when work is being done on the system, that's a positive value. Okay? You're getting a little foot rub, work's being done on you, whatever. Getting a pedicure, treat yourself, right? It's positive. All right, so for this, both of these, our gases are expanding. So both of these are doing work. And it even says which of the following performs more work. So both of these are increasing in volume. So expansion, both of these systems are doing work. But we're going to calculate which one's doing more using this formula. Okay? So for A, negative, our pressure is 2 atmospheres. And our delta V, what's our change? Always final minus initial. What's 4 minus 1? 3. Yay, we can do mental math. Okay? And now, what is 2 times 3? 6, and then we're going to make it negative. Actually, sig figs, just be negative 6. And I'm just going to leave that in liter times atmospheres. In a problem in just a couple, we will show you, I'll show you how to convert that to joules. Okay? And now we're going to do the same thing for B. What's my delta V for the second one? 2. What's 3 times 2? 6. So this one's also negative 6 liter atmospheres. So which one performs more work? Neither. They're the same amount of work. Okay? This is just showing you that even though the first gas, it's changing volume by more, it's expanding more, because its pressure is less, it's doing the same amount of work as this. So just showing you that it's not just volume, it's also pressure. Okay. Mm-hmm. Yes. Yeah. For now, yes. When we do our gas unit later in the year, that's when we'll review how to convert different pressure units. But for right now, I will always give you pressure in atmospheres. Okay. Until we review that. Cool. Okay. So now, how work relates? So we're going to calculate delta E. That's that internal energy of a system. So delta E is Q plus W. Remember, Q is heat. Yeah? So we're told we have an endothermic process. So endothermic, what does that mean my sign of Q is going to be? Positive. So we have a positive Q in which 8.69 kilojoules of heat flows. So that means my Q is positive 8.69 kilojoules. And then where 2.6 kilojoules of work is done on the system. So that's my work. We know it's 2.6, but what's the sign? Work is done on the system. System's having work done on it. It's a positive thing. Remember, when the system does work, that's negative. Work done on the system, that's positive. Okay? So to find delta E, what are we going to do with these values? Add them together. And deal with sig figs, your favorite. .3 kilojoules. Yeah, remember when you add, you're looking at place value, like decimal point, not sole number of sig figs. Cool? So like the math here was actually really easy. You're just adding. I just wanted to go over the signs. Now, for all of this, the sign, if it's positive or negative, all that tells us is the direction of, for example, heat flow or what's doing the work. Is it the surroundings or the system? Okay, so the sign tells us something, but for example, if I wanted to compare, like this is having 2.6 kilojoules of work done on it, okay? But if I had another system that was doing like, if work was like negative 5.7 kilojoules, that means this system is doing 5.7 kilojoules of work. This is still greater than the 2.6 kilojoules. So when you're talking about like magnitude of stuff, just look at the number. Don't look at the sign. The sign just tells us the direction of flow or what's doing the work. Okay? Let me erase that. All right. So this one, we're just going to calculate the work associated with the expansion of a gas from 15.3 to 26.4 liters at a constant external pressure of 1.5 atmospheres. So we have an expansion of a gas. What did I say that means about the work? It's going to be negative because when gases expand, they have to do that work to do it. Okay? In order for something to expand, they have to do the work. So to calculate my work, what's my formula? Yep, negative P delta V. So I'm just going to plug in what I have. Pressure is 1.5 atmospheres V, remember, it's, delta V is always final minus initial, so 26.4 minus 15.3. So go ahead and calculate that work. So since it's expanding, we should have a negative value. It's like good ways to just kind of predict what your answer should be. Sig figs, because we only had 2 sig figs for the pressure, so it'd be negative 17. And that's liter atmosphere. But now let's convert this to joules. The conversion is 101.3 joules equals 1 liter atmosphere. Okay, that's that conversion there. So to convert negative 17 liter atmosphere to joules, I'm just going to multiply by 101.3. And this is useful for if you, like in the last problem, number 5, we wanted to find delta E. Say you're given work information that you have to calculate work, and then you have to convert it to joules to then be able to add it to Q. What'd you get? Yep, negative 1700 joules, and that's my work. Cool? Questions so far? All right, so now let's talk a little more conceptually. Or I guess not necessarily conceptually, more mathematically. Being able to predict what your answer should be and be able to do some of this mental math is really useful for those multiple choice questions. Okay? So we're going to determine the sign of delta E for each of the following with the conditions that are listed. Now remember, delta E is Q plus W. Okay? Q plus W. So if we have an endothermic process that performs work, what sign does my Q have? Positive, because it's endothermic. And what sign does my work have? Negative, because it's doing the work. So we have the two things that have opposite signs. So when we add them together, the size of these values will dictate the overall sign for delta E. Okay? So when the magnitude of work is greater than the magnitude of heat, now my work identified as being negative, heat identified as being positive. When my negative value is bigger than my positive value, which one wins out? The negative. So my delta E will be negative. So we'd have an overall decrease in internal energy of the system. Where does that energy go if it's decreasing its internal energy? Where's the energy going? Into the surroundings. It's the system. It goes into the surroundings. All right. When my positive heat is greater than my negative work, what's my overall delta E? Positive. And then for B, we have work being done on the gas, and it's exothermic. So what's my sign for Q? Negative Q. And what's my sign for W? Positive. So when my positive work is greater than my negative heat, my delta E is positive. Oh, what did I just do? And when my positive work is less than my negative heat, negative delta E. So yeah, being able to predict those types of signs are really helpful for one, when you're actually doing calculations to make sure you're doing it correctly. Does your answer make sense? And two, it's a good skill for multiple choice. Okay. I'm actually going to stop the video here and start recording a new one because we're about to switch topics.